In this video, we are going to go over colligative properties, and we're going to go over qualitative colligative properties, so colligative properties without numbers, and then quantitative colligative properties. This year 2020, quantitative colligative properties are not going to be on the test unless it's bonus. So we'll do some of those, but just know that I need you to really focus on qualitative colligative properties. Okay, colligative properties are properties of a solution that depend on the number of solute particles that you have and not the actual identity of the solute. So one thing is vapor pressure lowering. Like if we have pure water, and imagine a hot tub, some of that water will be in the gaseous state, and that's considered the vapor pressure. If I, let's say, dissolve salt, like sodium chloride, in water, well, there's going to be less of these water molecules that can reach the surface and then become gas particles. So because of that, the pressure of the gas that is here will actually be less, okay? And so that's exactly why the vapor pressure lowers. With fewer solvent particles at the surface, fewer particles of water are able to enter the gas state, and so the pressure is going to be lower. Okay, we know less from last unit, less gas molecules means less pressure. Okay, now one thing is freezing point, and I'm going to draw a picture. It might be a cruddy picture, but freezing, you should know, is liquid going to the solid state. And so liquid might look like this. But when we go to solid, what's important is that these solid particles arrange in a way that is very uniform. Okay, solids are very, very ordered. So what happens is, well, what if we have some salt particles here? What's going to happen is it makes it more difficult to actually freeze your substance because you have salt particles that are there. And so these blue circles that I'm drawing, they're not able to get as close to each other here because the salt particles are interfering, okay? And what this is this is called freezing point depression. And if you have salt in your water, your freezing point will lower. Now, I'm going to do a calculation, and understand that the calculation is not something that you need to be able to do unless you're shooting for bonus. Okay, but I want you to still listen to the calculation and think about it, because we've got something called the Vant Hoff factor, which you should have covered in the last notes. But again, Vant Hoff factor is the number of moles of ions or particles that you have when you dissolve something in water. So this is the change, how much lower the freezing point is. Okay. Now, M is molality, moles of solute per kilogram of solvent. So, for example, if we had 5 moles of sodium chloride in 300 grams of water, molality is this italicized M. Don't focus on it unless you're shooting for bonus. We would say 5 moles of NaCl over 0.3 kilograms of water. Let me do that really quickly. 5 divided by 0.3. We get 16.67, and then not molarity, but molality. Okay, now, the Vant Hoff factor, just as a review, sodium chloride, NaCl, will break apart into sodium ions. You just look at sodium on the periodic table, it'll tell you its charge. Plus chloride ions. Again, look at chlorine on the periodic table and it'll tell you your charge. It's already balanced. We add up the coefficients, 1 and 1, so this Vant-Hoff factor would be 2. Just for argument's sake and as a good review, let's say we had calcium chloride. Calcium chloride is CaCl2. We get Ca plus 2 chlorides. We add the coefficients 1 and 2, and we get 3 as our Vant-Hoff factor. Okay, now, if you look at this equation, and I'm going to copy and paste this here. It's a good equation. What does, I'm going to move all the way down to B here. What does this formula tell us about the freezing point? Well, freezing point can only be lowered. So water's normal freezing point is 0 degrees Celsius. Okay, so we want to calculate the freezing point. So what we're going to do is we're going to solve for delta TF. It's going to tell us how low will it go, but it's not going to tell us the freezing point. It's just going to tell us how much lower it'll be than where it started. Okay, so the Vant-Hoff factor for aluminum chloride, we got to do AlCl3. According to the periodic table, we get Al plus 3 plus Cl minus 1. And to balance this, we need to put a 3 there for chlorine. So if I add those coefficients, 1 and 3, we get 4. So 4 is our Vant-Hoff factor. Kf is actually just a constant. It's a freezing point constant. So what I have to do is I have to go back up here, and I see, and this is the same on the back of your periodic table, it's 1.86 degrees Celsius times kilograms divided by moles. Okay. And those units are just so that my TF solves for in degrees Celsius. And then my molality, we've got 34.5 grams of aluminum chloride. I need to get that to moles. The molar mass of aluminum chloride is 133.33. And I get 0.259 moles of aluminum chloride. But molality is equal to moles divided by kilograms of solvent, which water is typically your solvent. So we've got 300 milliliters. 300 milliliters, if you remember from Unit 1, will be 300 grams. 300 grams is 0.3 kilograms. So our molality is going to be, let me plug this into my calculator, 0.2. Okay, 0.863 molality. And when I plug this in, 4 times 1.86 times 0.863, my change in freezing point, delta TF, is 6.42 degrees Celsius. Okay, so what does that mean? Water's new freezing point is negative 6.42 degrees Celsius. That's because this is telling you how much the freezing point changed. It starts at 0. It was depressed by 6.42 degrees Celsius, so water's new freezing point is 6.42. Okay, so if we look at this formula, what we know, and I want you to write some notes here, is higher Vant-Hoff factor equals higher change. And then higher concentration to us normally means molarity. Here it'll mean molality, but I'm not going to ask you on the test to calculate molality unless it's bonus. So higher concentration equals higher change. And I'm using the word change, and this is really important. I want you to understand this. We've just done freezing point, and we saw in our notes that freezing point is depressed. So freezing point lowers. And it only lowers, okay? Now, boiling points get elevated, okay, when you dissolve something in water. So let's think about this equation. This is going to be the change in boiling point. Water normally boils at 100 degrees Celsius. So this equation is going to tell us how much higher the boiling point will be, how much above 100 degrees Celsius. Okay, so delta TB equals glucose. Glucose is a non-electrolyte. What that means is our CHO element, C6H12O6, is a solid. It's just going to dissolve in water but not break apart. So we get 1 mole of product, so our Vant Hoff factor is 1. We're talking about boiling here, so we need to use the boiling constant, 0.512. And then our molality is 2.1 moles divided by 2 liters. Well, 2 liters equals 2,000 milliliters, which equals 2,000 grams, which equals 2 kilograms. So what we've basically proved is a liter of water is going to be a kilogram of water. And I'm going to plug this into my calculator. And I get delta TB is 0.5376. Kilograms cancels, moles cancel, and that's degrees Celsius. So under this situation, water's new boiling point is 100.5376 degrees Celsius, okay? And that's because boiling points get raised, freezing points get lowered. The magnitude, and this is what you're going to have to be able to do on the test, not bonus here, is that the higher the Vant Hoff factor, the higher your change is going to be, okay? So what is, let me erase some of this really quickly so it's out of the way. Oops. Higher boiling point, but lower freezing point. Again, higher concentration, same idea here. Higher boiling point, lower freezing point. Oops.